These are your constants that you decide from your initial conditions. What do I mean by that is, let's say that I'm just going to answer specifically the question that is raised right now. Let's say this is your equilibrium position and this is your maximum displacement when your x is equal to a, right? So these constants, when omega is another constant, but phi, the phase constant, is decided by your initial conditions. How we can do that is, let's say that someone did start his clock at this time, at t is equal to 0. Someone was at this position. Now, at this point, if I say that my xt at time t is equal to 0 was equal to a, and this is equal to a cos omega multiplied by 0 plus phi, right? So a is going to cancel each other out. You will have 1 is equal to cos phi, which is only possible when your phi is equal to 0. Or you can say that your phi is equal to 2 pi and so 4 pi, 6 pi and so on. But let's stick to the simplest forms here. Now, let's assume the second scenario when someone else came and he made the same measurement. He said that rather than starting from here, I'm going to start my clock from the equilibrium position. Remember, you are talking about an ideal simple harmonic motion. So you are saying that your system is going to oscillate for infinite amount of time by the same displacement, right? There are no dissipative forces. So if someone says that I'm not going to start my clock from here, I'm going to start my clock from here. Now, if you start your clock at this point, then you would know that if your particle from here, when it's at the equilibrium position, is it going to move in this direction or is it going to move in this direction, right? It can either be going in this direction or it could be going in the opposite direction, because your particle is also going to go here also, right? So let's say that he says that I'm going to start my clock when my particle is going to go in this direction, in the positive direction. That means your velocity is going to be a positive number, and let's say that is your VI, which basically stands for your initial velocity. Now, what would happen in this case? Now, let's apply the initial conditions here. At time t is equal to 0, now you are saying that your x is equal to 0. So, I'll have a cos 0 plus phi, right? And just give me a second. Okay. I just disabled. You people cannot write on screen now. So now your phi, you can say that your phi could be plus pi as well as minus pi from here, right? Every time your phi is either plus pi or minus pi, this condition would be satisfied. Your cos phi would be equal to 0 when your phi is equal to plus pi by 2 or minus pi by 2. But you have two solutions now. You need to pick up one unique solution out of it. Your phi can be either plus pi by 2 or it can be minus pi by 2. We can decide that. Now, if this is your velocity, if this is your displacement, then I can say that your velocity would be equal to minus a omega sine omega t plus phi. Now, from initial conditions, we said that your velocity is in the positive direction. Your velocity needs to have the positive sign. So now, if I say that my velocity at time t is equal to 0 was equal to vi, and this is equal to minus a omega sine omega t, t is equal to 0. So that terms becomes 0 plus phi. Can you tell me from here what would be the value of phi? The Vansh, I think he was the one having the question here.
मैम कौन किसका हेलो
हाँ जी
मैम किसको अनम्यूट करना है
it was Vansh, but just one second. I'm sure everyone knows the answer now. When your phi is minus pi by 2, then only your velocity will be positive, right? Because when your phi is minus pi by 2, you will have minus a omega sine of minus pi by 2, and eventually your minus minus would become plus. You will have a positive velocity, and that was your initial condition, that you wanted to have your velocity as positive. Now if you plug in the value of phi here in this expression for xt, you will get a cos of omega t minus phi by 2. You have decided the value of phi here. I can further rewrite it as a sine. Cosine is an even function. I can rewrite it in this way also. Oh, sorry, cosine here. I'm just writing a step ahead. And your answer would be a sine omega t. So that would be your particular scenario when your solution would be a sine function. And that's what I meant yesterday when I said that your sine and cosine are interchangeable function. By using this phi, which is your phase constant, you can convert your sine into cosine and cosine into sine. So you can start by taking your solution a cosine function also. Nothing is stopping you from doing that also. You can say that in this case also, I want to start with the solution a sine omega t plus phi. But in this case, when I was taking cosine, I said phi was equal to 0. But if you are taking here a sine, then your solution will not have phi is equal to 0 in that case. It's totally your choice whether you want to start with the cosine function or whether you want to start with the sine function. In fact, try doing it by using a sine function. Take solution as sine function and still say that your clock is going to start from x is equal to a at time t is equal to 0, and see what would be the value of this phi in that case. Do that by yourself and you will see that you can still justify a sine function also solution even when you are starting your clock from this point also. The only difference would be that your this phase constant phi, which we are taking 0 now, it would be a different number. हाँ जी विदित बताइए.
Good morning, ma'am. Actually, ma'am, I wanted to ask that, ma'am, कल हमने किया था, if the x is positive, then there will be deceleration and the speed will decrease, according to the expression.
If it is what?
If the x is positive.
If x is positive.
Yes, ma'am. Then there will be deceleration. Means the acceleration will decrease. The negative sign we did yesterday.
Yeah. Your acceleration will have the opposite sign.
Yes, ma'am. मतलब opposite sign होने का मतलब भी acceleration decrease होगी ना, deceleration होगी ना?
No, by saying that you are saying that your displacement is in this direction, your acceleration will be in this direction. Okay. If you have pushed it in this direction, then your acceleration would be in this direction. But is what you are saying.
Yes, ma'am. इसमें मेरा doubt था. But in the case when from the right extreme, when the object is going from the right extreme to the mean position.
Yeah. So this is your right extreme.
Yeah, when it is going to the mean position. Yeah, तो मैम तब same direction में नहीं होगा, जिस direction में उसकी movement है उसी direction में acceleration है.
No, because you are saying your x is equal to 0 is here. So even when you are here, your x is still positive.
Yes, ma'am.
Right? And your acceleration is going to be negative, in negative direction.
Yeah, okay, ma'am.
This was where we stopped in the last class, and I think we kind of already discussed these solutions over here. So this was where you have your xt, velocity and acceleration. Now, in this particular scenario, we are again starting our clock from this point. I'm saying at t is equal to 0, this was where my mass was sitting. That means your initial displacement would be equal to A, your initial velocity would be equal to 0, because at the extremes your velocities are 0. Now, from here, again, you can get the value of phi. I'm saying that at time t is equal to 0, your x was equal to A. That means you had A cos phi. That means your phi is equal to 0. So for this particular scenario, for which we are drawing the graphs of your displacement, velocity and acceleration, your xt is going to be equal to A cos omega t. Your velocity would be equal to minus A omega sine omega t. And your acceleration is going to be equal to minus A omega square cosine of omega t. So these are the three equations that we will be putting now. Now let's start at time t is equal to 0. Your x-axis is time in all the three cases. And the y-axis is either position or its velocity or its acceleration. So let's first focus on the position over here. What would happen is that at t is equal to 0, you will have x is equal to A. So this is your starting point here. Now let's take easy points from this graph. At t is equal to t by 4, what would happen? Your x would be equal to, at t is equal to t by 4, I can say that it's going to be A cos omega we defined as 2 pi by t multiplied by t by 4. I'm saying that t is equal to t by 4. So t will cancel each other out. You'll have cosine of pi by 2, right? Cosine of pi by 2 is 0. So that is why at t by 4, you will get 0 here. Now, if you put the value x is equal to t by 2, t is equal to, sorry, I am out of space. So if you put t is equal to your time, half of the time period, you will have at this point now. I'll have here t by 2. Again, what would happen is your t will cancel each other out. You will have cosine of pi. Cosine of pi is minus 1. So you'll have your amp displacement equal to minus A. And that is your this point here. Next time, put t is equal to 3t by 4. If you do that, you will get 3 pi by 2. 3 pi by 2 of cosine is again, cosine of 3 pi by 2 is again 0. So you will come to this point and the cycle will keep on going like this. Now, let's talk about the velocity, the next point here. At time t is equal to 0, your velocity would be equal to 0, right? Because your sine 0 is 0. So you will start with 0 velocity. It was easy to plot your displacement. The reason being that your initial displacement was here, so you could only go in one direction. But for velocity, when you start with 0, that's when the value for other values of t becomes important, because from here you can go upward or you can go downward also. In which direction you are going to move, you can figure that out by plugging in other value of times. For example, if I say that my t is equal to t by 4, from there itself I can get an idea from in which direction I have to go. So I'll have sine 2 pi by t multiplied by t by 4. T will cancel each other out. You will have sine pi by 2. And here you have minus. So your velocity is going to be minus a omega, which is the maximum value of velocity. And that's what will be deciding your direction. Now you know that you have to go in the negative direction, and now it's easy to plot the graph further for velocity also. You can try plugging in the other value of t also, t half, 3t by 4, and at least try doing it till your time is equal to 1 time period. Similarly, if you talk about acceleration here, so in the case of acceleration, what I can do is that, let's get rid of these numbers also. Now, your acceleration at time t is equal to 0 will be equal to minus a omega square. That means you will have negative acceleration at the maximum value. If you put time is equal to t by 4, you will have minus a omega square cosine of 2 pi by t multiplied by t by 4. Again, this will cancel. You will have cos pi by 2, and you will get 0 acceleration. So this will be the point where you will be reaching. And similarly, plug in the value of t by 2 and then 3t by 4 and t, and see if you can justify these graphs here. I would suggest that the case that we just discussed before the class, for one of the students' doubt, when we started our clock from this point, from the equilibrium position, plot these graphs, displacement, velocity, and acceleration for that scenario also. How would these 3 graphs are going to look like in that case? They will look different than these graphs, but still you should try doing it yourself. And let me just warn you, in the book Survey and Jewett, what he has done for the second scenario for which I'm asking you to plot the graph, by mistake, I think he has taken the cycle, time period cycle slightly wrong. There is a slight mismatch. You will see the graph and you will immediately know what's wrong with those graphs. Someone has doubt. Let's take the doubts later, a bit later. So now let's talk about the total energy of simple harmonic oscillator. I'll take your doubts in the last 10 minutes. Otherwise, I have to read the chat and come back here, read the chat and come back here. So if we talk about the total energy at any point, we know at the extremes, right? You know at the extreme, what would happen is that your velocity is 0, your total energy is potential energy. Also, you know at the center, that means at the equilibrium position, your total energy is in the form of kinetic energy. The potential energy is 0. But I would like to know what is the total energy in this case. And I would like to know that total energy is constant. That means your total energy should not be a function of displacement. It should not be a function of x. So we know what is the expression for the kinetic energy and what is the expression for potential energy, right? You know that your kinetic energy is given by 1 by 2 mv square. The potential energy is given by 1 by 2 kx square. You have already seen the expression for velocity and displacement. Now, if you plug in the value of velocity here, you will get a square, omega square, sine square, omega t plus 5. Right? This is your velocity square plus 1 by 2 k. X square is a square cos square omega t plus phi. We define omega square to be equal to k over m. That was our definition of omega square. Hence, I can rewrite this expression as omega square is k over m sine square omega t plus phi plus 1 by 2 k a square cos square omega t plus phi. M will cancel m. 1 by 2 is common. You can take it out. Spring constant k is also constant. Take it out. It's common in both of the cases. A square is also common in both of the cases. So you can take a square also out. You will be left with sine square omega t plus phi plus cos square omega t plus phi. This term is equal to 1. That means your total energy would be equal to this number here. If you look at this function, this is independent of x. That means your total energy is conserved. Your kinetic energy may be different at one position, potential energy may be different depending on at which point you are measuring, but their sum is always going to remain the constant. It is independent of how close or how further away from your equilibrium position is your mass. It's independent of that. And that's what has been done in this expression over here in the PPT. Now, let's plot potential energy and kinetic energy. We did plot your position, velocity, and acceleration as a function of time. Now, let's do the same thing for your kinetic energy and potential energy. This is your time t is equal to 0, right? At time t is equal to 0, in this case, again, your potential energy and kinetic energy graph would depend when you are starting your clock. If someone says that he is going to start his or her clock from the equilibrium position, then these graphs will be reversed. Because in that case, what would happen is that at this point, your kinetic energy will be maximum. Your kinetic energy would in fact be equal to the total energy. And the graph will be reversed in that scenario, right? Because if you look at this graph over here, the kinetic energy which is shown by blue curve is 0 at time t is equal to 0. Because we are starting from here, that is my time t is equal to 0. But if someone says that he is going to start his time from here or his clock from here, then this graph of kinetic energy and potential energy, they will be kind of interchanged with each other. That would be the difference here. Do that yourself and see what would be the difference. Now, let's talk about this particular case. When your time is equal to 0, you started your clock from here, your displacement was equal to your amplitude and your initial velocity would be 0 at this point. So your total energy, we said that your total energy is equal to 1 by 2 k a square. So at this point, all the energy is in the form of potential energy. There is no kinetic energy. If you go to time t by 4, this is your time t by 4, this is your time 3t by 4. Now, in time t by 4, what would happen is that you will come back to this position here. Let me remove this. Now, if this is your t is equal to 0, in time t by 4, your block will come back to its equilibrium position. And in its equilibrium position, its kinetic energy will be maximum and its potential energy would be 0 because your x is equal to 0. So at t is equal to t by 4, your potential energy has become 0. Now, what would happen? Your mass will go to the another extreme here. When it goes to the another extreme here, again your energy will be totally in the form of potential energy. At this point, your x is equal to a. So your potential energy would be 1 by 2 ka square. So hence at time t half, again your total energy is in the form of potential energy. At 3t by 4, what would happen? Your object will come back to its equilibrium position, and again potential energy would become 0. And when it completes its one cycle, it will come back to the position from where it started, and your whole energy again would be in the form of potential energy. If you talk about the blue curve here, at these points here, initially your kinetic energy was 0, right? What would happen? You come to the equilibrium position after 1 by 4th of the cycle. At equilibrium position, your velocity is maximum, and your all of the energy is going to be equal to your kinetic energy, and that is why at t is equal to t by 4, you will have your whole energy in the form of kinetic energy. At t half, you have again come to this point. You have your complete energy in the form of potential energy, and hence your kinetic energy would be 0. 3t by 4 maximum, and again at t you are back to the position from where you started, so your energy, kinetic energy would be 0. So this is how your kinetic energy and potential energy graph are going to look like. But if you sum both of these graphs, your energy is going to remain the constant. If you add both these graphs, you will get a straight line, and the straight line would be equal to 1 by 2 ka square, which is the total energy of the system. So this was graph which was showing your kinetic and potential energy as a function of time. If you talk about how your kinetic energy and position energy are going to look like as a function of displacement, you have maximum and the minimum, right? At the extremes, your kinetic energy is 0. At the center, your kinetic energy is maximum. And remember, kinetic energy is going to have a sine square formula here. That's why the graph looks like this. Whereas your potential energy will be extreme, at the extreme points, it's going to be maximum, and your potential energy would be minimum at the equilibrium position. Again, if you add both of these parabolas, your sum would remain constant, and that would be equal to 1 by 2 ka square, which is equal to the total energy of the system. Okay,